So good morning, everyone. I'm Nando. I'm currently at University of Michigan. This work was done over at New Mexico State University. This is a joint work with William Yeo and Rick Pontelli. So let me start right off with some motivation. This is a talk about multi-agent systems, and we're motivated by the recent development of a variety of applications, starting from service-oriented computing to distributed control of fleet autonomous vehicles to the deployment of smart sensors and smart home control, where essentially we have multiple agents which needs to coordinate their actions to optimize the global objective, and they are often subject to some user preferences. For instance, in a smart home development, you may have some preference about schedulability of certain objects. In addition, in many of such application agents, they need to solve complex problems, and as the instances grow large, the dynamics of those agents translate into hard combinatorial problems, and thus posing significantly challenges from a computational point of view. So in order to combat such a challenge, in this talk we're going to exploit the power of GPUs, which are parallel machines, so to speed up resolution of those solvers. And in particular, GPUs are increasing movements, and it can be used to accelerate non-graphical application, with some example domain that have benefits from this type of hardware, ranging from bioinformatics or sequence alignments to machine learning and numerical analysis, to mention a few. So I'm now going to provide some background on multi-agent discrete optimization and Markov Chain Monte Carlo algorithms. I will present some details on the GPU and GPU model, execution model, and then I will summarize our contribution. So this is going to be very high level, details are in the paper, and I finally will present some results and derive some conclusions. So a multi-agent constraint optimization problem is formalized as a set of variables, each of which can take values from a set of finite domains. And then we have a set of constraints, which are represented in form of a table, where for each combinations of the values for the variable in the scope of the constraint, we express some utility, which can also capture the notion of preferences. And those entities are distributed among a set of agents, as you see in the illustration here, which coordinate the assignments for the variable that they control. Now, in particular, we are interested in certain type of configurations where agents have to deal with large problems, and this is some assumption that actually we're breaking from the general assumption that has been held in the community, where agents deal with the single variables. And we argue that that assumption is actually restrictive because there are many domains where agents need to deal with complex problems. And also, we've shown this in last AAAI, this can be very inefficient. So here we differentiate among two sets of variables. We have local variables, which are the variables that are involved exclusively into intra-agent constraint. And we have the yellow one, the boundary variables, which are variables that are involved in some constraint shared with another agent. Okay? So the goal of the problem is for the agents to coordinate a joint assignments for the variable they control, so to maximize this utility function, which is the sum of all the constraints in the problem. And this is done via message passing. So every agent communicates with its nearest neighbor, given a certain network topology. So communication is localized, objective function is global. Now, since our solution employs Markov Chain Monte Carlo sampling, let me briefly tell you what MCMC algorithms are and why we can use them to solve discrete optimization problems. So Markov Chain Monte Carlo methods are a class of algorithms for obtaining a sequence of random samples from a probability distribution from which direct sampling might be difficult to derive. And so as you see here in the example, if we want to approximate this red distribution here, we can start from a proposal distribution, the pink one, and this would generate the Markov chain of samples, each of which will depend from the previous sample, using a proposal distribution which will point out which one could be the next point for the random sample. Okay, and as you can see in this example, the quality of the sample improves as a function of the number of steps. So why we can use MCMC for solving discrete optimization? Well, especially for distributed constraint optimization, this is a result from Yen et al. In AMAS 2013. Essentially, there is a mapping from solving a distributed constraint optimization problem to a maximum a posteriori estimation problem, which is what you can solve with a sampling algorithm. And now this process, I mean, the process of sampling can be costly, given the type of sampling algorithm that you choose. And also, it might require a lot of samples to converge. So in this work, we are going to investigate the use of GPUs to speed up this process. So let me tell you a little bit about the GPU model. A GPU is essentially a massive parallel architecture. It has thousands of computing cores, and it is designed for performing computing-intensive operators. I think that about 80% of the transistors in a GPU are devoted to data processing rather than caching or flow control. So CPU and GPUs are very different. CPU cores are fast, GPU cores are slow. In CPU we have fast access memory, in GPU we have different levels of memory, typically very slow accesses. So GPU programming can be very challenging, and in order to derive some successful application, it requires a thoughtful understanding of the hardware. This is the execution model. So we call a kernel a function which can run on a GPU. It is executed on some threads. So a thread is a basic parallel unit. It's a work unit of the GPU. Threads are grouped together in blocks. Typically, a block contains 1024 threads. And then blocks are scheduled together for execution in streaming multiprocessors. So a GPU has a scheduler which schedules together several streaming multiprocessors at the same time, which means that all in all, you're going to schedule a set of threads, typically in the order of 10,000s. The GPU parallel model is based on what is called the single instruction multiple thread paradigm, where essentially threads execute exactly the same instructions, all of them, but they may operate on different data. So we need to satisfy this condition. Let me briefly show you how a typical GPU program works. Here we're using CUDA that are API provided by NVIDIA. So we differentiate with the host. We denote host as for the CPU and the device as for the GPU. A typical CUDA program is a mixture of C or C++ instructions as well as CUDA calls. The execution typically starts with enforcing a data flow from the host to the global memory of the device, whose access are extremely slow. Then, once we have this data in the memory, we can run our kernel function, which runs on threads, and the results are written back on the global memory, and then they can copy it back on the GPU memory, on the CPU memory, on the host, which can continue its execution. Now, I will talk about our proposal. I'm just going to introduce earlier this related work, which comes from Yen et al., where the authors used in MCMC algorithms for solving distributed discrete optimization problem. They use Gibbs sampling. So essentially, Gibbs sampling is approximate a joint probability distribution over all the variables of a problem when only marginal distributions are available. Think that we want to solve a problem that is the sum of all the constraints of the problem. We only know the single constraint. Okay. So in the centralized Gibbs works as follows. We initialize the set of all the variables with a random assignment, and then we run for a sequence of samples. Within each sample, we're gonna sample one variable. We're gonna work on one variable at a time. And when we're working on this variable, the proposal distribution for that sample depends on all the previous samples for all the other variables that are involved in the process. Now, a challenge for Gibbs is that it requires the conditional distribution the target to be sampled exactly. So here there is a hidden normalizing constant that might be computationally expensive to compute. as well as in the distributed version of the algorithm, the one that the author presented, essentially the agents needed to concurrently samples and communicate their choices with all their neighbors because those choices may affect their own successive samples. So, which means that this results in a lot of communication and slow convergence. So we're going to take a different approach here. We're going to exploit the structure of the problem when the agent has multiple variables, starting from the following observation. So if we fix the value assignments for all those boundary variables here, we are actually left with a problem on the local variables of the agents that agents can solve independently from each other. Okay? So what we're going to do is the following. Imagine that we can bundle up all the choices for all the boundary variables, and in this way, essentially, we are left with a single problem for the local variables that agents can solve together. So we can use a dynamic programming method to solve the problem over the boundary variable of the agents, similarly as what we do with bucket elimination. Actually, the distributed version of bucket elimination is called depop. And now, essentially, we don't need that much communication. We just need a linear number of messages for solve the whole problem. But however, we are left with these internal problems here, which can be they are typically NP hard. So what we're going to do there, we're going to use Marokv Chain MCMC algorithms. And specifically, we studied Gibbs sampling and Metropolis-Hastings in this work. The reason why we're doing so is because those type of algorithms are really amenable to parallelization, and I'll show you why. So this is the general schema of our parallelization. So if you notice, each row of this table here, actually the value computation of each row of this table are independent from the computation of the other rows, right? So we can use a set of blocks in order to compute each row of this table in parallel. And this is similar to what we explored last year at this venue, where we proposed a dynamic programming algorithm for with the constraint satisfaction and the COPS. Since the MCMC sampling procedure is stochastic, then we can run a number of different samples for a particular value choice of the boundary variables, each of which can start from a different point, so with a different random start. And this is because the chain might converge faster, right, with a different start. And then we are going to use a block to compute each of these samples. Within each block, we're going to use threads to compute in parallel the actual operations of the MCMC algorithm. So for instance, in this case, for the Gibbs sampling, we are going to use a number of threads which is equal to the size of the domains of the variable being processed. Okay, in this example, for instance, assume that we are processing variable xk, assume that variable xk domain has size 3 with values 0, 1, and 2. So we're going to use threads with ID 0, 1, and 2 to compute in parallel the proposal distribution of when xk takes value 0, when it takes value 1, when it takes value 2. And we're using an analogous method to also compute the normalizing constants. So now, notice that this process is very amenable to the GPU model, as the threads execute exactly the same instructions but on different data. And in particular, we take great care on ensuring that the data access pattern that we enforce is coalesced. Coalesced here means that multiple threads running with contiguous ID are going to access some data in the global memory which reside in a contiguous location. So remember that access data to global memory is expensive. We typically spend 400 clock cycles for one read. And when we do this type of operations here, with a single read, we can serve up to 32 threads. And instead, we want to discourage this type of pattern here, because we will need multiple threads, and then, multiple reads, and then the threads might be serialized. Additionally, when computing the utility tables, we use a simple perfect hashing to map utility table row indexes to values of the boundary variables. And this is to avoid to store all the possible values of those variables in the global memory. So we just then use the index to derive those values. This saves space and this saves time to access to the global memory. So some results. I'm going to explain some of our analysis on first runtime of our algorithm for CPU and GPUs, and on then solution quantities at the increasing of the number of samples. All plots are in logarithmic scales. So for this plot here, we have two algorithms, the Gibbs sampler and the Metropolis-Hastings in gray, so the Gibbs is in black, where continuous lines are the CPU version, the dotted lines are the GPU version. The general message is that we can obtain at least 1 order of magnitude speed up with respect to the CPU version, which is nice. In terms of quality, we compare our GPU versions against a complete solver, the red line, and one of the most highest performing incomplete solver, MCMC, which is this blue line, which denotes the average result, and those are error bars. So we can see that our Gibbs sampling process here has very high quality results compared to MGM, starting from a number of samples that is relatively low for this particular example, of course. While Metropolis-Hastings solution quality is comparable to that of MGM. And of course, we run several experiments. More details are in the paper, but just to summarize the main message here. So if we focus on what MGM, the blue line, does, and what our GPU Gibbs sampler does, we can see that the Gibbs sampler consistently outperforms. So it finds a utility of higher value with respect to those of MGM, with the time that is up to 2 orders of magnitude less. So instead for, Metropolis-Hastings, actually it's even faster than Gibbs. However, the solution quality is not as competitive to Gibbs. And this is also because Metropolis-Hastings requires some tuning, and so we actually didn't spend that much time in tuning this algorithm. So to wrap up, we exploited a GPU-style parallelism from dynamic programming-based methods, as well as MCMC sampling. We were motivated by the assumption that most of these distributed constraint optimization algorithms are, the agents essentially control single variable. We were motivated by the recent introductions of sampling algorithms for solving this type of problems, and on the availability of GPUs. So we introduced the distributed MCMC framework, which decomposes the problem into independent subproblems that can be sampled in parallel with GPUs. And we show that some of our samplers can obtain higher results than the best incomplete solver with up to 2 order of magnitude time faster. So this type of technology can actually also be applied to the centralized case, in particular to weighted constraint satisfaction. And in the future, we plan to explore this direction, as well as extending our proposed method to deal with the memory requirements. So right now, the memory requirements are still, we're suffering still the same memory problem that a bucket elimination algorithm would suffer. So the computing of the table would be exponential in the induced width of the problem. But we are planning to run some memory-bounded algorithm to solve this issue. So thank you for your attention.